Hello. The purpose for this video is to demonstrate how a commercial finite volume code such as ANSYS CFX can be used to model a steady convection diffusion problem. For this, we're going to look at fluid flow and heat transfer over a circular cylinder. You can imagine a very long cylinder in crossflow. And this is an interesting problem because it takes on so many different forms depending upon the Reynolds number. At very low Reynolds numbers, you have steady laminar symmetric flow. At a little bit higher Reynolds numbers, you have flow that's still laminar and steady, but now there's this recirculating region in the wake of the cylinder. At yet higher Reynolds numbers, the flow is still laminar, but now it's transient with these detaching eddies in the wake. At even higher Reynolds numbers, the flow becomes turbulent and transient. And at even higher Reynolds numbers, the flow can be almost thought of as turbulent and steady. We're going to focus on this laminar symmetric case about a Reynolds number of, we'll use about 26, I believe, in this analysis. But you can see we have symmetric flow about a center line here, and the flow separates and circulates immediately behind the cylinder in the wake. We're going to try to model this using ANSYS CFX. We begin by opening ANSYS Workbench, and under the Analysis Systems toolbox, I will choose a Fluid Flow CFX template. I can just left-click and then drag that into my project schematic to create a template through which I can build the analysis. And I will start with the geometry. In Design Modeler, I've chosen centimeters for my unit system, and I will begin by creating a sketch of the fluid flow domain. So I will come over to my XY plane, and I can right-click and choose to look at that. And I can move from my Modeling tab to my Sketching tab. Now before I draw, I will click Settings, and then under Grid, I will show it in 2D. So now you can visualize the grid, and I will snap to the grid to help me draw more clearly. I'll go back now to the Draw tab, and I will choose the rectangle icon. I can click and use my scroll wheel to zoom in. I can hold the Control button and press my scroll wheel on my mouse to pan as well. And I will start by clicking at my origin once, and then I will move up, and I want to go about 10 centimeters high. I'm sorry, about 2.5 centimeters wide. Since it's snapping, it'll snap to 3, and then about 10 wide, and I will left click again to finalize that. Now even if the dimensions are not what I want, I can easily change that by clicking on the Dimensions toolbox. And by clicking, I can establish a vertical dimension and a horizontal dimension. So for horizontal, 10 centimeters is what I want. For the vertical, I wanted that to be 2.5 centimeters high. And there I have my rectangle. The next thing I want to do is extrude that. So I will click on my extrude icon. It's asking for the geometry, so I will choose my sketch and apply. Add material. I'll use all the default options except for the depth. Since this is going to be a 2D analysis, I don't need to model in the Z direction, so I will just extrude a small distance. How about 0.05 of a centimeter? And I see the lightning bolt symbol, which means I've yet to generate that, so I will click the Generate button. And now you can see I've created a thin solid, which will represent my region of fluid flow. Okay, the next thing I need to do is to create my cylinder and subtract that from the solid. Now I'm modeling this using symmetry is my plan, so I only need to model half of the cylinder. I will go back to my XY plane, and I'm going to create a new sketch. Let's see, where is that? Right here. I'll move to my sketching tab, and this time I'm going to draw a circle. There we go. I'm going to put my circle 2 centimeters away from the front of my domain. One click, and then I just move my mouse out to establish the diameter. I want it to be 1 centimeter in diameter. So again, I can switch to my dimensions, and it automatically grabs the diameter. I'll change the diameter to 1 centimeter. Now, if you needed to change the placement, we could also use the Dimensions tab to change how far this is from the front face. Okay, I'll go back to modeling, and I will extrude this time. Extrude Sketch 2. And instead of add material now, however, I want to cut material. And I will move in the same direction. I have the lightning bolt symbolizing now I can generate that. And you see that I've subtracted that from my fluid domain. So now I have a region in which I can model fluid flow symmetric about the top half of my cylinder. At this point, it would be very helpful to go ahead and establish some boundaries for later identifying my boundary conditions. I can do that by rotating to look at the front, which will be my inlet, and I can click on that front to highlight the face. I can right-click and choose Named Selection, and for the name, I'll choose Inlet. And note, I still have to hit the Generate button. I can do that again for the outlet. So I've highlighted the face, right-click, Named Selection, and Generate to activate that. The top of my fluid domain, I will just call Top. My bottom is actually symmetry, so I will choose these two faces, one, and I'll hold down my Control button, choose the other one as well, right click. I will call this, how about Sim Bottom, for the bottom symmetry. Note that I have two faces selected. I can generate that. My cylinder, I can click and highlight the surface of the cylinder. I'll just call that cylinder. Let's see. I think I have two regions left, and that's going to be the front face and the back face, which are both symmetry faces. I'll just call this Sim Front. And then I will rotate to the back side. And I'll call that Sim Back. Okay, so I have my inlet, outlet, I have the top surface, the bottom surface, the surface of the cylinder, and then I have the front and the back faces labeled as symmetry. There's one more thing that I need to do at this point, and that is in anticipation of meshing. I want to have a finer mesh in the region right behind the cylinder, in the wake region. And to do that, I'm going to go ahead and create one more body in anticipation of doing that mesh refinement. So I need a new sketch. I'll click on the new sketch icon. I'll move to my sketching toolbox, and I'm going to draw another rectangle. And I'll just move down here 1 centimeter below the center of my cylinder. And I will just extend this to 1 centimeter behind the exit of my domain as well. Okay. Again, I could put dimensions if you want to move this around accordingly, but right now I think this is good. So it's 2 centimeters high, and then 1, 2, 3, 4, 5, 6, 7, 8, 9 centimeters long. I will now extrude this. Now my geometry is sketch 3. Okay. Instead of adding material, I want to add frozen, which is going to not combine this with the other domain. Everything else should be fine, and I can generate. Okay, so if you note now I have two objects, and those are located and listed here at the end. Two parts, two bodies. The first one, I'm going to rename this, since this is my fluid region. And then the second body is the body I'm going to be using later on for mesh refinement. So I'll just call this something descriptive, maybe refined mesh region. Okay, so I've created my geometry through which I can model fluid flow and heat transfer around this infinitely long cylinder. I can at this point save my project, give it a descriptive name, and then I can open the meshing application. So I've closed geometry and saved my project. I have a green checkbox next to that cell, so I can move on towards the mesh now. Double-clicking will activate the meshing application. Now I'm in the meshing application, and I notice that it has correctly imported the geometries that I've just built. And so now I need to give it commands to appropriately split this into a region of control volumes through which I can use my finite volume method for a numerical solution. So I will click on Mesh, and relevance I will move up to 100, which increases my default mesh size, or decreases it, I guess rather I should say. And on advanced sizing function I will just use fixed. And on relevance center, which also changes the mesh size, I will choose fine. Everything else there I will leave as a default. I can click the update button, and that will incorporate those changes and give a first go at a mesh. Now this is probably enough elements in the vertical direction, but I know I will have large velocity gradients where the fluid comes in contact with the wall of the cylinder due to viscosity, the effects of fluid friction. So I need to change mesh settings for that as well. The first thing I'll do is right-click and I'll insert a method. For my geometry, I will choose my fluid flow body. And on the method, I will choose sweep. Since this is a essentially 2D problem, I'm just going to have one element thick in the Z direction. I will change from automatic to manual source and target, and then for my source I'll choose my front face. For my target I will rotate to the back and choose the back face. And then for the number of divisions, instead of the default, I will force it to do only one element thick through in the Z direction. Okay. Now let's add some inflation. So I will insert inflation. The geometry, I'm going to use my front face of the fluid domain. For my boundary, I'm going to grow the mesh out from the edge, so I will choose the edge from the cylinder. Instead of smooth transition, I will choose a total thickness. So for my inflation, I will set 10 layers. The growth rate, which is the multiple of size of the next layer of elements from the first, I'll choose 1.1. And the maximum thickness of my layer, I will choose 2 millimeters. Okay, so I can click the update button and incorporate those changes now into my mesh. Zooming in, you can see that now I have a very small element size near the surface of the cylinder, and that is growing out. I don't want such an abrupt change there, and I need smaller element sizes around the cylinder also. So I'm going to make a couple of extra changes. One, I'm going to right-click on Mesh, insert a sizing, and for my geometry, I'm going to choose the cylinder edge again. There I go. And for element size, instead of the default, I'm going to make that 0.5 millimeter. 5 times 10 to the negative 4th meters. Let's update that again and see the change that that makes. Okay, a little bit better. And then one more thing, I'm going to use this body to refine the mesh where I know I'm going to have a wake behind the cylinder. I will go back to Mesh, right-click, I will insert another sizing. For my geometry, I will choose front face again. And for the type, inside, let's see, oops, actually, for my geometry, instead of the front face, I will choose the whole body. And then for type, now that changes and I have body of influence. So essentially, this body is going to influence the mesh on my fluid region. So for the body of influence, I will choose that extra rectangle. Okay, and for element size, I'll make that 0.5 millimeter as well. Now let's regenerate our mesh. I'm back now that the mesh generation has finished, and we can observe what's happened. So the mesh is indeed refined in that wake region. Now, by default, the meshing application is trying to use quadrilaterals for the mesh, and we can see that's resulting in some weird things going on. So for that, I might go back to my sweep method, which is where that is selected, and you see the free face mesh type is a combination of quad and tri, and I can change that to all tri, which will replace this with triangles. So I can hit the update button once again and let that remesh. Okay, that looks a little bit more uniform and workable for us. So we see that we have a small mesh at the surface of the cylinder, which is what we would like. That expands uniformly. There are no large discontinuities. And in the region behind, or in the wake of the cylinder, I have a finer mesh. Further away, where I expect not much to happen, I have a larger mesh. For statistics, I can scroll down and activate that, and I can see that I have 11,428 nodes, or 10,761 elements. Okay, and I'm done with my mesh at this point, so I can close and save my project. Okay, I double-clicked on Setup, and that opened CFX Pre, which is the preprocessor for my finite volume solution. It automatically brings in the geometry and the mesh. You can see that. And I'm going to work my way down top to bottom, essentially in overriding the default options when necessary and establishing the materials and boundary conditions and solution processes for this problem. So moving down, I'll double-click Analysis Type. I want steady state, so I will leave that as it is. Now default domain, I can double-click on that. It automatically has obtained the body, which it's assuming is a fluid. That's correct. For the material, I will indeed choose air at 25 degrees Celsius. It's a continuous fluid. I'm not using any buoyancy. Under fluid models, for heat transfer, if I look at my options, I can turn that off completely. I can choose isothermal, everything at the same temperature, which would not create any heat transfer as well. thermal energy and total energy. Now I'd use total energy for compressible fluid flow since I'm using low velocities, much lower than a Mach number of 0.3. I can use thermal energy. I am not including viscous dissipation. Under turbulence, I'm not using that yet, so I'm solving the Navier-Stokes equations as laminar fluid flow. I'm not going to use any combustion or radiation. Under initialization, I will just click that to use automatic initialization. So for my first guess as to the solution, the computer will just use a simple interpolation based on my boundary conditions. I'll choose OK. Now I need to insert my boundary conditions. So right now there's just a default, and that will go away once I have correctly listed something for every boundary. So I will right-click, Insert Boundary, and the first one will be my inlet. And this is the nice thing about using the named selections. I can just type inlet, and it goes ahead and grabs that location from the possible faces. My inlet will be subsonic, and for normal speed, again I said I was wanting a Reynolds number of about 26, so I went ahead and calculated that, and I'm going to need a normal speed of 4 centimeters per second to create that. Since I am using heat transfer, I need to establish heat transfer boundary conditions as well, so I will assume the flow coming in is at a steady static temperature of 25 Celsius. Okay, and we see that it has established that boundary condition. Why don't I do the outlet next? So I see it's correctly grabbed the outlet of my domain. Now for my mass and momentum equations, I will choose a static pressure and make that 0 for my relative pressure, 0 pascals. And that is essentially saying that there's no more pressure change at the outlet. In fact, there's no more gradient as well. Everything is steady at the outlet. You can think of that as a Neumann boundary condition where the gradient is 0 as well. I choose OK, and so that boundary is established. I can establish the boundary at my cylinder. Okay, and now the cylinder is a wall representing my long infinite cylinder, and on boundary details I will make it no slip, meaning velocity has to come to 0 at the surface. And on heat transfer I will choose a constant temperature, and I will set that to, I believe I was choosing 50 degrees Celsius. Okay. The front, back, and middle lines are all planes of symmetry, so I need to set those as well. And I can call those out. I had sim bottom, so I just choose that as symmetry, and note that it takes all the other options away as a result. It's just reflecting whatever occurs. I see that, and I can insert that for the front and rear faces also. Okay, I still have default domain there because there's one more surface I have not specified a boundary condition for, and that is the top. Okay, for the top I have a couple of options. One, I could use a opening boundary condition and set a opening temperature, opening pressure. Another option, since I've made this very large and I expect only horizontal velocities, nothing vertical at that point, so no mass is going to enter or leave. I could also set that as a wall. And instead of having velocity go to 0 at the wall, I can make it a free slip wall, meaning there is no friction on that surface. And if everything is uniform in temperature as well, there is no temperature gradient, thus there is no heat transfer. And I can set the adiabatic option for that as well. Okay, and we note the default option has disappeared because all of my boundary conditions have been set. I don't have any interfaces, so I'll move down to the solver. In terms of iterations, I could just have it go to 100 and then it will stop, and if that's not good enough, I can restart the solution. I'll just up this to 300. For the timescale control, that's affecting the solution process, and I'll leave it on its default automatic settings. For my convergence criteria, I will set my target to 1 times 10 to the negative 6. And then since heat transfer is involved, it's good practice to set a conservation target as well, and this is 1%. In other words, the solution will not stop until conservation of energy is below 1% error at all of the boundaries. Okay, I will leave everything else default on that. On output control, it's always good to monitor the things of interest in your solution. So I will activate monitor, and under points and expressions I will create a new monitor. The first one I'd like to look at is heat flux from the cylinder. So I'll call it maybe average heat flux. And instead of a location, I will choose an expression. And you'll have to take it on faith that this expression is valid. I got it from just post-processing over time, understanding. You can also learn these expressions using the help literature with ANSYS CFX. But I will take an area average of the wall heat flux at the cylinder surface. Click Apply. If there were an error in my coding, that would have showed up in my message box. Okay, I'm wanting to calculate the heat transfer coefficient, so I'm monitoring my average heat flux to see when that converges in the solution. And then I will add another monitor, and I will call this drag force. Again, that will be an expression, and for the drag force caused by the cylinder in the crossflow, I will calculate force underscore in the x direction. Again, this is an open and closed parentheses, and then at and a location, and I will choose my cylinder, which is the name I specified in the geometry earlier on. Click Apply. It accepted that as well. Okay, so I think I've gone through. I have set up my default domain with its material. I've set boundary conditions for the solution, and I've changed the solver control, including monitoring two things of interest. I can now save this and go back to Design Modeler. Okay, and the next thing is the solution. My step now is cell 5, which is the actual solution of the discretized algebraic equations created by the preprocessor. So I will double click to activate, and that will open the Solver Manager program. Now that that's open, under my initialization option, I will leave that the default. And that's just saying that if I run the solution multiple times, it will use the previous solution as a starting point. The initial value specification is handled automatically then. And I can choose Start Run. And that should activate the solver. Any minute now. Here we go. The first thing you'll note as I scroll upward is that CFX pre is just a graphic interface to create the text file that is input that sets up my material, boundary conditions, all those things. So you can observe them at the top of the solution file. Now on the left-hand side, what you are observing are the residuals as the program is trying to solve the coupled algebraic equations, coupled simultaneous equations for, let's see here, we have conservation of mass to solve for pressure, conservation of momentum in the x direction, in the y direction, and in the z direction. The z direction is dropped off since this is a 2D problem. There's essentially nothing to solve in the z direction. And I'm watching the residuals as I go from one. This is a fake time step, so you can think of this as an iteration in the solution process. While that's going on, I can also look at the heat transfer tab, and I see that this is solving H energy, enthalpy. We can see now that that's dropped below my specified target. Okay, and all of the others have as well, and I'm told that the solver run finished normally. And it took about 73, 75 steps. Now the user points also shows the monitoring points that I created. I can right-click, choose Monitor Properties, and to help me see sort of scaling, I can look at the average heat flux. I'll click Apply. And you can see that that started very high and then quickly after about 20 iterations moved to a more steady value. Under range settings, I can set a manual scale, and maybe let's go from 0 to 500. Apply that. Okay, maybe 150 to 250. Apply that. And so you can see it took about 40 iterations for the average heat flux from the cylinder into the fluid to basically hit a steady converged value. What about the drag force? I can apply that, and under range go back to automatic scaling. That seems to have stabilized as well after about 10 or 20 iterations. So I can override this scale. And I see there's not much change at all. It took maybe, let's say, 30 iterations for the drag force to stabilize. So going back and looking, that's corresponding with a maximum residual error of 1 times 10 to the negative fourth. Okay, so sometimes this doesn't mean or doesn't inform us of much when we're looking to calculate solutions of interest. Using monitor points can help you accurately understand whether the things of interest to you have converged or not. We'll also look at the resulting file. It tells us information about our mesh, the size of it, and how okay the shaping of it is. Okay, for each iteration I'm told the residuals in terms of the root mean square and also the maximum value of the equations that I'm solving. So I have my conservation of momentum, conservation of mass for the pressure, and conservation of energy for the enthalpy or temperature. It's also giving me information about the linear solution, which is taking any nonlinearities in the equations and solving those. And so I have this summary for every iteration, all 79 that it took. In the summary, it tells me that all target criteria reached for the residuals I specified and the global imbalances. And it tells me, so for instance, conservation of momentum in the x direction, it tells me momentum over the cylinder, the inlet, and the outlet. It sums those together to determine the total imbalance terms of conservation of momentum, and I see that that is less than, what is that, 1/10,000th of a percent error. It does that for the V momentum, the W momentum, conservation of mass. You see I have a very low error, and then conservation of energy. I have a 0.3% imbalance if I apply conservation of energy between my cylinder and my outlet. Two places where heat transfer occurs. I have other summaries as well. At the end, it tells me how long it took to solve the process as well. Okay, I have all this, so I can close it. Now that my solution is complete, I can now enter the post processor, which will allow me to take the solution and perform calculations of interest, including plotting for visualization. So I will double click on the results cell to open CFD post. Okay, now that CFD post is up, I can begin to manipulate my solution. The first thing I'd like to do is visualize what's going on, create a report of that as well. First, let's visualize the mesh for reporting processes. Since I have symmetry, I would like to go ahead and just mirror what's happened here on the bottom. I can do that under user locations and plots through the default transform. I can double click to activate that. I want to apply a reflection. That's grayed out, so I need to turn off the instancing info from domain. And then my reflection, I want to reflect what's happening on the, let's see here, I guess XZ plane at y equals 0. Let's apply that and see if it does. Yes. There I go. Okay. Now for my mesh, I can click on the front face and show the mesh on that. So that would be sim front. Right now it's blue. I can double click to open the details. And I can click to rotate through the colors. I'll just choose white. And then on render, I'll move down and activate the show mesh lines. Okay. So now I have a view of my mesh. If I want to take away the gradient on the outside, I believe I can go to Viewer Options, and instead of a gradient, I can just use a solid white color. There we go. So I can center it in my view as I would like it, and then I can right-click and choose Copy to New Figure. I can just call that Figure 1. And then you note it has copied everything I've done into a new figure and placed that in a report. Okay. Now, another thing I can do if I want to keep this open, I have 4 different views I can move through, plus the figure that I've now created. So I'll move to a second view, and I'll click on Z to orient that in my view field. The next thing I might like to do is view what's happening in the velocity field. For that, under the user locations and plots, I will right-click and insert, and let's insert a vector plot, for instance. I can just call this maybe velocity vector, for instance. And under the details, I will plot on the front face, which is sim front. The thing I want to plot is velocity. Let's go ahead and apply that and see what the default looks like. Okay, so I can zoom in if I would like. And it's using color as well as size of the arrows to indicate magnitude. And then you can see that indeed, as flow is going over the cylinder, near the surface, the velocity decreases due to friction. And then in the wake, you can now see a rotation set up. Okay, I'll zoom back out. And if I'm preparing this for a report, I need to work with the legend. And you can see that this is sort of bulky in terms of giving the velocity. I don't really want scientific notation. I can fix that by clicking on my default legend view. I can move my legend around. So I might center it, for instance. And under text parameters, I can change that to fixed notation. Okay, that looks so much better. Under definition, if I don't want that velocity vector, I can just change it to variable. I can orient this a little bit better. Okay, and I have a nice velocity plot as a result. If I like this, I can right-click and copy this to a new figure as well. Another way of showing velocities is through a streamline plot. So I can right-click, insert, and I will choose streamline. Okay, my velocity vector is still turned on, so I can click to deactivate that. Now for streamline, I will start from, and I have different options I can use for that. I'll choose the inlet, which is where I should start for since the flow is coming in through the inlet, flowing over the cylinder. Okay, I see streamlines indicating lines tangent to velocity, and I'm not picking up the recirculating region just yet. I need to work from a grid pattern in order to get that. I see that that's too fine, so I need to go in and reduce that. Let's try 0.05. Still no. Okay, I'm getting there. Okay, you just have to use trial and error to figure out how this works. Actually, I think what I need to do, since I'm doing a grid now, is I want to grid the front face. Change my spacing accordingly. There we go, and maybe aspect ratio, have that as well. Okay, so now we have a more reasonable streamlined picture, again with a nice legend to go with that. And if I like that, I can right-click, copy to new figure, figure 3. Okay, I'll move to a nice new blank view. Another thing is I've solved for pressure in my domain, so I can look at the resulting pressure field. A good way to do that would be to insert a contour plot. For my locations, I'll use the front face again, and a variable will be pressure, and I can apply. Okay. And I can see as a result, as I would expect, I have high pressure at the very front center where the fluid comes to a stop, stagnation pressure. I would expect pressure decrease as the fluid has to accelerate as it travels around the cylinder. The lowest pressure region is right before flow separation. Flow can't turn the corner anymore, and then I have a lower pressure region behind in the wake. And I can see that these things have, I've given them sufficient distance to work themselves out. I have lower gradients in those regions. Again, the legend is not very clear, so I will double click on that. These are really small pressures. They're actually more millipascals. So before I do that, why don't I go to the Variables tab, I can click on the pressure variable, and if the units aren't good for you, you can change them to many different settings as well. Let's see. Nope. Pascals, I think it's going to be for me. So I can go back to my outline, my default legend view, and under appearance I can change that notation perhaps. Maybe a little bit better. That's up to personal preferences. Okay, so I can orient now my pressure map, and if I like that, I can copy it to a new figure. The final thing would be temperature, since I was solving the conservation of energy equation as well. So I could just take my contour, and instead of pressure now, I can plot temperature. Again, I would see what I would expect. The cylinder is hotter at a constant temperature of 50 Celsius than the surrounding fluid, coming in at 25 Celsius. And so there's heat transfer through conduction and advection, meaning total convection into the fluid. And I see wake region dissipating behind. Okay? And again, this legend is not very legible. Under variables, I can change temperature, for instance, from Kelvin to Celsius. That helps. And then on my legend view, I can change my appearance to fixed and then reduce my precision as a result. Maybe 1 decimal place. Okay, so I have my maximum temperature 50 degrees on the surface of the cylinder, my bulk fluid temperature 25 degrees, and then I have variations of that in regions where heat transfer occurs. I'll right click and copy that to a new figure also. It might be helpful at this point to actually view the report. I can click on that tab. Here's the outline of it, and then I can scroll through. It gives me a nice summary of the file, the meshing, the physics that I set, the boundaries, and then here's the user data, the figures and plots that I've created and imported as well. And if I wanted to save this, I could click on Publish and save it as a HTML or web file, for instance, to open in a web browser. That would also save the images to work with also. Another way to save images would be to double-click on the figure, I believe, and then right-click, and I could save the picture that way also. That's a lot better than just doing a screenshot. Okay, the last thing I'd like to do is to calculate the convection coefficient for heat transfer from the cylinder into the fluid. And then I'd also like to calculate the coefficient of drag of the cylinder in the fluid crossflow. Let's take care of the heat transfer coefficient first. Now, calculations can start under the Calculators tab. The function calculator is one way that you can learn the different function commands that CFX uses in the post-processor. So for my convection coefficient, I can take the flux divided by the temperature difference between the surface and the fluid, and the result must be my convection coefficient. Well, how could I find the heat flux? One way I could do that would be an area average over the entire cylinder face of the cylinder. And then the variable, I can click on the ellipsis button here to pick up all the possible variables. And then I see that there's actually a heat flux variable. I can click the Show Equivalent Expression, and it will show me the code expression that generates the result. So I see that on average I have a heat flux of 200 watts per meter squared at the face of the cylinder. Oops, I could copy that, for instance. Now I can go to expressions. I can right click and create a new expression. Might call that heat trans coefficient, something meaningful. And then I can put in my definition. So Control V will paste, and if I click apply, that reproduces my heat flux. To turn that into the convection coefficient, I need to divide that by the temperature difference. I set this boundary at 50 Celsius. I set my free stream at 25 Celsius, so the difference must be 25 Celsius or 25 Kelvin. You have to use units, so put those in brackets. And there I go. I have a heat transfer coefficient of 8 watts per meter squared Kelvin. Another thing I could do would be perhaps to take the area average at the inlet of temperature, and I could get this 50 degrees by taking the area average of temperature at this surface. So I can code that in directly if I also want, for instance. The drag coefficient is a little bit more complicated. For that, let's see, I'll create a new expression. Give it a meaningful name. Now the drag coefficient is the drag force divided by the projected area that the cylinder shows to the flow, divided by 1/2 density velocity squared. Okay, so I need to calculate that here. First thing I need is the drag force. So I can use force underscore x at the cylinder. Again, I could find this using my calculator. And you see, this is how I learned the monitor points as well in CFX Pre. So there's 6 times 10 to the negative 9th newtons of force created by drag. Now remember, I've only modeled half of this, so I need to double that because I have 2 halves of my cylinder. So there's 2 times. Okay, and that is appropriately doubled. Now I need to divide this by the area that I present to the projected area to the oncoming flow. Okay, if you remember, my diameter is 1 centimeter, and I extruded 0.05 centimeters into and out of the z-axis. So my area would be 1 centimeter times 0.05 centimeters. Since I'm putting in units, ANSYS will correctly take care of unit conversions as needed in the calculations. I also need to divide by 1/2. I also need to divide by the density. I could type that in directly, or I could calculate it. I'll just use area average of variable density at the inlet. So that's a good way of grabbing the value that ANSYS is using. And then I need to divide by the incoming velocity squared. So for that, area average of velocity space u, meaning the horizontal component, at the inlet. And that velocity is squared, so caret 2. If I've done this right, the drag coefficient should be unitless. So I'll click apply, and there we go. I get a drag coefficient of about 3 for this cylinder in crossflow. If I want to add that to my report, I can do that in the, let's see here, I can right click and insert a table. And then here I could, for instance, say heat transfer coefficient, maybe drag coefficient, and then in B I can insert that expression. Okay. And with that created, I can go back to my report viewer and refresh it. Scroll down to the bottom, And let's see. The drag coefficient was not inserted. There we go. Refresh one more time. Okay, and now I have a table that's taking in my calculated heat transfer coefficient and my calculated drag coefficient. If I didn't like the number formatting, I can change that accordingly through one of the commands up here. Here we go. I think this is the formatting button. Scientific may be fixed. There we go. Okay, and with that, I've used CFD post now to post-process the numerical solution to obtain plots and graphs, and also to obtain calculations, in this case drag coefficient and the heat transfer coefficient. Now I'm done.